Good afternoon, everybody. Welcome to the fourth seminar in the Freeze and Tell or FT webinar series. This is a series that we organize once in 2 months. This is organized by the ANRF Cryo-EM facility at IIT Madras. I'm Mamta Bangera, and there is Manikandan and Anirban. We are from the facility. And we have a speaker today, Professor Somnath Bhattacharyya, who is a faculty at the IITM. I think Mani will be having a short introduction for you. You're muted, Mani.
Hello, welcome you, sir, and thank you all for coming. This is the fourth seminar of the series. Today's speaker is Professor Somnath Bhattacharyya from Metallurgical and Materials Engineering Department of IIT Madras. He obtained BE in Metallurgical Engineering from VNIT Nagpur in 2000, and then he did an ME in Metallurgy from Indian Institute of Science, Bangalore. After that, he got his PhD in Material Science from Max Planck Institute for Metallurgy in Stuttgart in Germany. Then he did a postdoctoral work in few laboratories like Virginia Tech and then Leibniz Institute for Surface Modification in Leipzig. And then he was working in TA4 as a leader from 2009 to 2015. He joined our institute IIT Madras in 2015, and then from 2020 he's a full professor here. And his research activities covers STEM method development, simulation, and experiment, which are interdisciplinary in nature, and it spans over material science, physics, chemistry, and nanoscience. And currently, he and his groups are doing research to establish correlation between synthesis, local atomic and electronic structural properties of wide range of two-dimensional maxi material, like two-dimensional inorganic compounds. And then he has been recognized for his work. He was selected as a Andalusia Talent Hub Fellowship in 2015 from Spain, the government of Spain, and he is an editorial board member of Scientific Reports since 2014. And then welcome you, sir. Today he is going to talk us about atomically resolved 3D reconstruction of nanostructure from single projection using inline 3D holography. Sir, please continue.
Thank you very much. Can you hear me?
Yes.
Thank you very much. Thank you very much for the introduction, and thanks for inviting me to present my work here. So today, most of the people may know about atom probe tomography. So you generally what do you do in while we do imaging? We get information, 3D information in 2D. That's imaging. So if we want to get information in 3D, so we can get 3D structure at in atomic resolution. How can we do that? That is the work I'm going to present. It's called inline 3D holography. So this method which I'm going to present, it was previously developed by Purang Chen and Van Dyke, but this was actually developed for very high-end microscope, which has a spherical aberration and chromatic aberration character, and the sample is hanging when there is no supporting film under the sample. So we tried to we thought how to bring it back, bring it down to the level where normal microscope can be used, high resolution microscope can be used. So this is the and then we did the modification in the method. And when you are doing you are studying nanoparticles, you generally you dropcast it on carbon film and you see that. So I will discuss also that that creates problem. So what is the effect of that? This then we developed according to that method was modified, and here I'm going to present that thing. So first, when you do this 3D structural reconstruction is called tomography. So 3D structural tomography reconstruction. One thing is atom probe tomography, which we know, and this national FPT is facilities here in our institute. So, but FPT has its mass spec. So it has its own advantage, but disadvantages also. because there could be escape of atom during acquisition, then artifact generation due to sample preparation. This limits the this atom probe tomography, especially when you are working with very small structure, nanostructure, let's say 10 nanometer or below that. Now, we can look at electron tomography. In electron tomography, also using TEM, we can get 3D structure. We can do it in both the modes, in TEM mode and STEM mode, means in parallel illumination, parallel static illumination, and convergent rastering illumination. But if the STEM tomography is more common, especially for biological people, but so electron tomography has its advantage that sample preparation is easier. You can have a pristine structure with respect to atom tomography, but STEM tomography has its own limitation because you have to tilt the sample along the axis. It should be 180 degree, but you cannot tilt up to 180 degree because you have pole pieces, upper pole piece. So there is a missing wedge, and that affects the result. Okay, and STEM means high electron dose rate and high electron dose rate per pixel. So for electron beam sensitive sample, it is dangerous, it is detrimental. And another thing is that alignment of tilt series images in a common axis. So these are the limitations for STEM tomography. So we were interested with TEM tomography. What is TEM tomography? That you take images from in one projection, you take an image at different defocus, and from that you can determine the 3D structure. And interestingly, I will show that you can go up to 0.4 angstrom resolution in Z direction. So sub pico 400 picometer resolution you can achieve there. Actually, we achieved that, so we will show that. And in TEM, the advantage is that you can reduce the electron dose rate. So and you are taking images at multiple images, so noise doesn't matter. Noise will be reduced, and then that is the advantage. So you can use the for electron beam sensitive sample also. Now, what is the motivation of this work? As I previously said, this method was developed by previously by Chen, and it was published in Nature Communication before. So, but generally, when we do, but that method is basically for material which has no support. Now, think this way. When we are working with nanoparticles, generally we broadcast it on carbon. Now, if we broadcast in a carbon film, actually it imparts the it imparts strain. There is no strain in the nanoparticle, but you will see strain if you measure the strain in the material. Yeah, if you calculate it from your high resolution image, you will see that. What is the reason? Because your electron beam passes through your sample and then it passes through the carbon film. So what is your exit phase wave, which contain your material specific information, that is again get distorted by that supporting film, and that's why if you increase the, so we worked pretty much on this direction before, and we found that if you increase the amorphous carbon film thickness, your this strain or despacing variation increases, which is actually an artifact, imaging artifact. So so we try to see if we can do inline holography, 3D holography with a nanoparticle sitting on the carbon film, how much it affects. And this method was tried only for so this method had some limitations, and this method inline 3D holography was tried only on simple cubic structures. We tried it for non-cubic systems, the hexagonal and tetragonal system. So for some technologically important complex nanostructure like quantum dot metal oxide nanoparticles, to see how we can get the 3D structure from one dimensional projection. You are seeing the material from one direction. So that is the method. So if we try to see the objective, the study, first thing objective was to study the influence of amorphous carbon support on tomographic reconstruction of nanoparticle from single projection. Second is that we have done it for indium nitride quantum 3D structure of small indium nitride quantum dot less than 10 nanometer in X and Z, and reconstruct the atomically resolved 3D anatase TiO2 nanoparticle. So these are the three objectives, or the three different examples I will show. So what is the method? This actually, so this schematic gives you an idea of what it is. So you have incident wave. Incident wave, if you go for wave equation, you have plane wave, so phase is 0. Now it goes through the sample. Now, now think this way: if it goes through the sample and it's a homogeneous sample, let's say the homogeneity level, homogeneity is below the the level of homogeneity is below the wavelength of the electron beam, which is in picometer, then you will see that there is no change in the phase of the exit phase wave, because it's a thin sample, so amplitude doesn't change much. So amplitude, we should not worry about amplitude, mainly phase. Now, but if you think about a crystal, even a single crystal, you have atomic column, and in between two atomic column you have around 1 angstrom difference, but your the wavelength of your wave is in picometer. So so for the electron which is going through the atomic column and which is going in between the atomic column, that will have different speed, because they will get different hindrance, so there will be a phase change, and that's why you get you see the in exit wave or exit phase wave, you will see change in the that will have change in phase of the exit phase wave. So at different in x and y direction. So it's called exit phase wave. And if you think in that way, ampere in the and why this phase change is happening, because of the inherent electronic nature of the material. So it means that all my material specific information is actually stored in the phase of the exit phase wave. And so if we can get that, we'll get all the information about the material. And then it goes to the lens system. So lens imparts its aberration are there. So it imparts aberration. So finally you get more distorted wave. And finally, what you take as an image, then image means I. So phi multiplied by phi transpose. So your phase information is lost. It's only amplitude square. So the idea is to, from image, how can we get the phase of the exit phase wave? So there are different ways. You can go with off-axis holography, and I work with inline holography. So I developed a method in my PhD that you take images at different defocus. From that, using iterative approach, you can determine the phase, retrieve the exit phase wave. It's called FRWR algorithm. So many people use that nowadays. So it so you are getting the exit phase wave, and then this reconstruction, or the inline, this is called inline holography or exit phase reconstruction, exit phase wave reconstruction. So then we coupled it with electron channeling theory. What is electron channeling theory? So electron is going, if you refer to the image in the right hand side, so electron is going through the atomic column, and so it will have dynamical scattering, and dynamical scattering means more than one scattering, and then when it is channelized to the atomic column, it will focus somewhere, then it will again defocus. So it will it looks like the lens. So that distance is called extinction distance. And electron channeling theory works. Actually, electron goes like this, and through the material. And electron channeling works when there is a the difference between two atomic columns should be more than 1 angstrom, because below that, the electron from one channel, electron from another channel, they will interact with each other. So you cannot use electron channeling theory. So the basic of electron channeling theory is that the channel, it should be channelized. They should not interfere within the material. Okay. So how this method works? So let us first reconstruct the exit phase wave. So any method you can use to reconstruct the exit phase wave. So this is the wave image of a wave, exit phase wave. So you have column and you have the gap between the column. The phase of the wave of the atomic column is called it's called column wave. and the wave of the gap or valley is called valley wave. And now the wave of the vacuum is called the wave of the vacuum is called background wave. Now when you there is a I gave the reference here. So as you increase the specimen thickness, your valley wave changes, so as your channel the column wave. So with increasing thickness, your valley wave should be 0, no? But if it's not 0, it should be everywhere. It should be same, but it is not same when you are not using a CC corrected machine, means chromatic aberration. So that's why first we need to normalize the column wave. So you see the equation here. So column wave is normalized with respect to the valley wave, and then it is subtracted from the background wave. So that is your background subtract. Now you see this sample. This is the bottom surface of your sample. So for now, this is my background subtracted wave. But if I want to know the wave exactly here, like here, exactly at the exit phase, then I have to move this background subtracted wave for each of the atomic column. I have to move it up or down. So how to know where what is the exact Z height? So there is a work done before, which is called that. This is so Furong Chen, Mendy came up with the equation in 2015 that it's called maximum propagation intensity criteria. So you your reconstructed wave you actually propagate in vacuum, and so at where you have the maximum intensity, that focus value is the exact focus value of that atomic column. So if you come here and for each of the atomic column, if you get the exit phase wave, then you are getting the bottom surface geometry. Okay, so bottom surface geometry we got in a series structure. Now is the atom count. So I got the bottom surface geometry. Now I need to know how many atoms are there. So how to do that? So this bottom surface geometry, the focus at for the column wave at each of the atomic column is called focus corrected wave, because you are correcting the height. And now you can plot it. It's a wave, so it's a plus ib. It's a complex number, so it's called Argand diagram. You can plot it here, and now you need to know for each of the. So this is real, this is imaginary. You can plot it here, the wave value, and then you need to know for one atomic atom, what is the wave. So you have to get that wave there. So you can't do it in experiment, so you have to do it by simulation. So how to do the simulation? You have to it's a multi-slice algorithm. Using multi-slice algorithm, you can do that. But here we have to understand. We have to keep one thing in mind. Electron dose rate is very important. So we are talking about phase of the wave, means phase, how the phase changes, because electron is seeing the electrostatic potential multiplied by the thickness. Now when we calculate this potential is called mean inner potential, let's say, or electrostatic potential. For each of the element you can get an electrostatic potential. Now the electrostatic potential we calculate, it's actually using frozen phonon approximation. So at 0 Kelvin. But when you are hitting that, your atom is moving. It's actually vibrating. So the phase value is the potential is smearing out. So phase value is getting reduced as you increase electron. So electron hits the sample. It hits up the atom. So it reduces the. So as you increase the electron dose rate, your phase value gets phase of the exit phase wave, or phase the electrostatic potential. How you explain it? It gets reduced. So how to incorporate that in the simulation using Debye-Waller factor? This is the mean square displacement. So using the electron dose rate, that changes, and that's why your Debye-Waller factor changes. And from that you have to simulate You have to take just 1 minute. I am showing one example here. Okay, I'll show this, but it's like here you see, you have to simulate a structure like 1 atom, 2 atom, 3 atom, 4 atom, 5 atom, and you have to simulate the exit phase wave and the phase of the exit phase wave. So you will get the value for each of the atomic column. Now, when you get that, you plot it here. You can plot it here, and then you divide this theta dash value with theta value, means focus corrected wave value by the angle, the focus corrected wave value by theta, and you will get the number of atoms in the projection direction or in your electron beam direction. So that's your 3D structure. Now, our interest was to see this is the method which was developed by Furongchen and Van. Now, our interest was to see how this method works when there is amorphous supporting film for the nanocrystal. So we have simulated a structure. This is a carbon film. You see a carbon film here. This was done by MD simulation, and this is a crystal structure. And this crystal is a silver structure. Now silver, we have taken the same height here. I'm showing, but we kept this value 3.6, but we changed the AC, means amorphous carbon film thickness. We changed it gradually, so it's very small thickness. So per particle, this is the particle thickness 3.6. This is amorphous carbon thickness is more, and you see that gradually this is the same which is showing here. Amorphous carbon thickness and particle thickness. Here amorphous carbon thickness is leading. Here it's more, and here generally this is different carbon amorphous carbon density, and is different amorphous carbon density. So we have simulated that. Now the crystal we have simulated, it's a cylinder. Why cylinder? Because it will be isotropic, so there will be no directionality, and it's half the way it is hanging. So so you can directly compare the inline 3D holography data or tomography data from unsupported and supported region. And we have taken silver 100, okay, 001, so or 100 silver. So you have two types of atom, B and AB stacking. So 9 atom and 10 atom. So this is what we so we try to see the increasing carbon film thickness and density. That is one thing. Second thing is that the method, actual method, they have used this value wave. As I said, this is very important. This value wave, they have taken any value wave around the atomic column, but that is with a microscope with CC character. But here this will change. So what we have done, we checked both the things, a single, and we have taken average everywhere to see whether that changes or not. And also we changed the nanocrystal from silver, copper, gold, and this is less and this is more atomic number, to see whether that has any effect on this 3D tomography. This is completely simulation work. So this is the imaging parameter we used for our simulation. This is the focal series acquisition parameter we used for our simulation. Now, what is the when we are talking about defocus? Since we are taking the reconstructed wave up to the each of the atomic columns, so there is that we have to do some normalization. Since this is sitting on a carbon film and we know the carbon film thickness here for simulation, so we subtracted that to get the normalized, and for each of the atomic column now we can take it up. So that's all. So presence of carbon. So this is our simulated structure, and this is the so when we did this simulation, this is the after focal series reconstruction, the exit wave reconstruction. This is the phase of the exit wave reconstruction. This is unsupported view region. You see, as you increase the carbon film thickness, your unsupported region, the reconstructed phase is getting more and more distorted. And it is also evident from the Argon plot. If there is no support, then you will see all the points from each of the atomic column. It is lying on the argon plot. But here you see, as you have disturbance for carbon film thickness, it will go outside. It will be diffused. This spot, the points will be diffused, and as we increase the carbon film thickness, we are seeing this thing. This is also evident from the bottom phase geometry or focus map. We are now I'm using focus map instead of bottom phase geometry, and this is the atom count. You see, this is the unsupported region. This method works pretty well. When it is supported with amorphous carbon, as the carbon thickness increases, we are not getting the same value everywhere. We are seeing there's a lot of variation in both for the focus map and the atom count. Now, this whatever I have shown there, it is graphical representation. As you see, unsupported region, it's showing only 9 and 10 atoms, and there is a defocus change of -0.1 and +0.1. If you see the structure here, this is showing also the same thing. But as you increase the carbon film thickness, both are getting diffused. And even if you compare this one with this, the density of carbon, more density of carbon, you see this is also changing a lot. Now, I'm coming to the point of value wave selection, which is very important. So we did the same thing, TP by TSE, or it's 1:1 carbon film thickness and the crystal thickness, and we have taken one-dimensional line scan. And now this is for the value wave. So these values, so we took the single value wave. You see, in unsupported region means here it is flat, but in supported region it is this blue one. It is varying like anything. This is the single value wave. But if you take the average value for each of the atom around each of the atomic column, you see the variation gets reduced. And this is the focus, the column wave. Column wave in the unsupported region, here it's exactly accurate, same like value wave. Here it is varying too much, but when we are taking the average value wave, the variation gets reduced. So it means if we take average value wave when there is a carbon support, it actually reduces the error in the final data set. Now the same thing, single value wave selection, value wave selection, and if this is the phase mass map. Sorry, this is the defocus map. This is the atom count or mass map. And now, if we see the defocus error with average value wave, it's very low, but single value wave it's quite more. It's only 0.25. It is around 0.4. And you see here also, if you take the atomic column calculation, average value wave, this error is less than the single value wave. So averaging the value wave reduces error in the defocus and atom count in this calculation. Okay. Now we changed. Instead of silver, we tried with copper and gold, and we didn't see any change. So what is the take-home message? First of all, if we have carbon film thickness, it actually affects your inline 3D tomography reconstruction. So you cannot get the exact. So it actually distorts your tomogram. And yeah, your the bottom surface geometry or focus and mass mass means atom count increases with increasing carbon thickness, no matter what is the atomic number of the crystal is. So these are the take-home message of this. So then the simulation. Now this is experimental. So this is a silver nanoparticle, and if you see here, it's carbon here. So this is fully supported. This region is partly supported, and this is unsupported region. And we have done the same thing. You see the unsupported region, all the spots on the argon plot. Here it is deviating. It's partially supported and it's fully supported. So this deviation is more. So this is the focus map, and this is the mass map. you can see here for all three regions, and this is the variation, the histogram is showing for each of the atomic color. And it shows that this method gives, and this is the focus corrected wave phase value. So here you see the atomic column for the thinnest region, or which is unsupported. It's 6 to 10 atom, and it's varying like, and here this focus corrected wave variation, and here you see here everything, all atomic column, all atomic number of atoms, it's having the same number of atomic columns. So it means that you have more error when it is fully supported. And if we calculate the thickness accuracy from the net focus, if you see the thickness accuracy, the unsupported region, this gives you in z direction atom, your z direction, your the atom count is accurate up to 0.4 angstrom, or partially supported 0.6 angstrom, and fully supported 1 angstrom. Here we have to understand one thing, that the structure, the thickness of the amorphous carbon film is around 3 to 4 nanometer. So the experimental data now we have. This is the 3D structure, and if you see here, this region 3 is actually matching with our simulated data, where TP by T is equal to 1. This is a simulated data. These are more or less same, because here average thickness is 3.5 nanometer, and carbon film thickness, from the manufacturer is 3 to 4 nanometer. So that's why we are seeing same type of whatever we saw here, that the background and the bottom surface geometry and atom count, we are seeing the same type of problem here. So what is the take-home message of this full work? This was after experiment and simulation. So so Valley wave selection is very crucial. So averaging the Valley wave is reduces the error, and increasing carbon thickness or density, it imparts error in your the focus calculation, or the bottom surface geometry calculation, and atomic atom calculation. So your tomogram. And atomic number doesn't play an important role in all these things. So whatever atomic number your nanoparticle is, it works. But it depends on the curve. So we should not, if we are trying to do 3D reconstruction, we should always try to have a carbon film thickness which is lesser than the crystal thickness. That's a key factor. Then you are much more accurate. Now this is one example on small indium nitride quantum dot. Okay, so this is experimental data. It was done on sorry. So it was it is a experiment which was done with a negative CS imaging. So atomic columns are bright, and depth between the atomic column is dark, which is different in a non CS corrected machine, objective lens CS corrected machine, because they are mainly, if you see the contrast transfer function, atomic columns are dark, and gap between the atomic columns are bright. Okay, so this is purposefully this was done, because then we can see atomic columns. So it's very easy to find where we should focus. That's why. So this is the experimental condition, and so you can see here this bright spot is actually indium, and this comet-like structure, it is actually nitrogen, and the distance of indium nitrogen distance is 1.1 angstrom, more than which is needed for this electron channeling theory. So, but we focused on indium nitride because we need the focus corrected focal column wave, and we can take the peak point of each of the atomic column. But for nitrogen, it's not possible because it's a diffuse structure. So we focus on. So here we got a spatial resolution of 0.8 angstrom, and this is the one image, and this is the reconstructed phase of the exit phase wave. And you can see this is the MIP criteria, the intensity, so which defocus I have to take for one of the atomic column, and this is another atomic column. And argon plant, you see there is a lot of deviation. This is because there is a thick carbon film. And this is the defocus map, and this is mass map, and this is a histogram for each of the atomic column. We have taken all the atomic column. And now this I have already shown. So how we calculate to get the quantum that so for single atomic column, what is the focus corrected to calculate that, because I needed this to calculate the atom count, do the atom count. And this is the another quantum dot. Here the resolution was different. It was calculated from the if anybody is interested, it was calculated from this G max. So here also the same thing, bright column is nitrogen, indium, and this diffuse thing is nitrogen. And we have taken this region because this has a different direction. This is 112/0. We were interested there, so this is diffuse map and mass map. Now you see, we didn't touch the mass map. We didn't try to correct the mass map. We try to do some correction for the defocus map. So we see what we have done. So this is the two indium nitride nanocrystal, and we know that the atomic columns which are in the periphery, each layer has different, it will have different thickness. It is the thinnest at the edge, and then it comes into the thickness into this or this quantum dot. If you take a quantum dot and see it from the hemisphere, so at the periphery only, but all atomic column will have the same height there. So what we did, we calculated we take the atom count for each of the atomic column here, for the carbon number 1, carbon number 2, carbon number, all the carbs, and then the mean value and standard deviation, and which atomic column, like this is going out of this. So we actually take this average value and we replaced with that value here, this atom count. The same thing we did here. So that our background, our bottom surface geometry is correct. And this is the 3D structure of both the tomogram of these two indium nitride quantum dot. So we found that it's a pre-pyramidal shape of this indium nitride quantum dot, which matched with the theory, the theoretical calculation. So that is one example. Another example is TiO2 nanoparticle. So this is in one direction. So this is the experimental. So this is the experimental condition. This is a resolution you can see here, 1 angstrom, and we have done the same thing here for both the regions. And this is the atom count, and this is the defocus map. And what we have done here also, we have done this correction. So each of the atomic columns should have the same thickness. And the one layer is same thickness, then the second layer R2, then R3, R4, and we took the average value and standard deviation, which is going up and down, like this one. We substituted with the this average value, and this is the 3D structure for that. Okay, so this is the tomogram of this, and we did for another two structure, 110 direction also for this type of TiO2 nanoparticle, and 001 and 010. This is the two sets of data, and so here it's only titanium. So these are only I didn't consider oxygen here because the atomic column has the value that it's not very focused. That's why. But this is this 010 is as this. Each of the atomic column is comprised with titanium and oxygen. So we did it for both. And when we took all the data together for TiO2, it is coming. It is coming as a truncated tetragonal bipyramid, and this is actually this data actually matches well with the theory developed by Zhang and his co-workers. So just about nanoparticles. This is a 3D structure, and so this work which I'm showing, it is one of my former student Pritam's PhD work, and my another student Chiranjeev, my other students Chiranjeev and Sundro, they also helping so there should be Dr. Sundro Gandhi. So they were involved in the work, and this experiment, all the experiment, so theory we have done, then simulation we have done, and also the data analysis. But the experimental was done with in University of Cadiz with my old friend Professor Francisco Morales in his group, and his students were also involved in correcting the experiment. Thanks to them, and special thanks to Professor Furong Chen and his co-workers to help us initially to understand this inline 3D holography so that we can do the modification, and our financial assistance from SCRB. And finally, thank you very much for your kind attention.
Thank you, Professor Somnath. I think so. If there are any questions, please go ahead. Maybe you can type it in the chat as well, and I can read it out. Or if you raise your hand, you can ask your questions as well. So maybe, Mani, go ahead. You want to say something? Okay. I think there's some interference that's coming in. So maybe I just, I mean, I'm from the life sciences background, so this might be a very naive question. But can you detect defects in the crystals and fractures through this technique?
See, this technique is giving you the 3D structure. So whatever will be there will be detected.
Okay, okay. So you should be able to.
So like atom probe tomography. But this method we tried, frankly speaking, we tried with only with crystalline structure. We didn't try with non-crystalline structure because our knowledge on biological sample is, and actually you don't need anything in for biological sample. The minimum, I did some work in the beginning, long back in Virginia Tech. So you don't need a resolution of that level. No? So you are happy with the resolution of, let's say, 10th of nanometer.
Yeah, yeah.
We are interested of sub-angstrom resolution. So there is a difference in. But this method can be used for biological sample as well. Yeah, but we have to do the calculation. Means we have to modify the method according to that.
Okay.
Some modification is needed.
So in biology, okay.
Sorry, you can't take this method and you can take the image and do this thing. But first of all, one thing you can use electron channeling theory also in biology because okay, your the atomic columns, there is no atomic column in that way. That is one thing. So there should be some modification in the method because it's not like it's
arranged.
Yeah,
yes.
That is one thing. But there is the advantage is that within two atoms you have more than 1 angstrom gap.
Yes.
So that is an advantage, but this is disadvantage.
Okay.
So some modification is needed.
Okay, okay. Also, we have very weak phase objects. Ours will be generally carbon, hydrogen, nitrogen.
Weak phase object actually easier than a phase object.
Okay.
When you are talking about crystal, it's a phase object.
Yeah, yeah.
And that's weak phase object. The equation is simple. You don't have to write sigma psi equal to AR e to the power I phi R. That equation, you can write it 1 plus this, that way it's easier.
Okay.
But any equation, even weak phase object, you can explain it as phase object using amplitude 1. Actually, from my experience and calculation, I found that if you working with nanocrystal, nano means I'm talking about real nano, below 10 nanometer or 10 to 20, so that region, because I'm interested in that region.
Yeah.
There, actually, everything is weak phase object, you can say.
Okay.
So you can safely use phase object approximation.
Okay.
Phase object and weak phase object, it doesn't matter because your amplitude is so minimal. You can take as 1.
Okay. Nice. Anybody has any questions?
Sir, yeah, Subrata.
Go ahead. Sir.
So I have 2 questions. One is, so this is only for perfect crystalline material, right? Not for non-crystalline material.
Yeah, I actually, when I worked at, I see, non-crystalline material, you have to tweak the method a bit.
Ultimately, there has to be column of atoms, right? So
no, when there is not a column, then the equations will be a little bit different. But if the atoms are this, yes. See, the column means okay. So let's say my atom. Okay, you cannot. So you will have an atomic column like this, yes. or if it is going like this, you can make a column. You can think of a column like this. But the next atomic column which is coming, means whether you are thinking of a
yes.
column or string, there the gap should be less than not less than 1 angstrom. If less than 1 angstrom, then you cannot use it. Then you cannot use this method because then electron channeling idea will not work.
I have one technique, another technique, like question that came to me that if that is for basically highly crystalline material. Now you take a material where is some portion is crystalline and some portion like, let's say, some crystalline material embedded within biomolecules.
Okay.
So for that kind of for that kind of systems, will this inline 3D holography will work, sir? Yeah.
Yeah. See, for the crystalline material, I can say yes. So then
I'm saying that, let's say 10 nanometer or yes, 10 nanometer nanoparticle embedded within the biological.
Yeah. So if you assume biological sample as a supporting film, that means it's okay. So for the nanocrystal, you can perfectly do that. If you want to use the that also in this equation, see, this is so if you are taking purely biomaterial.
No, sir. I am taking bio as well as.
No. I'm separating it out.
Yes.
So let's say you have this is your biomaterial. Here you have a nanocrystal.
Yes.
Okay. So when you are working in that nanocrystal zone, if you want to see the 3D structure of the nanocrystal, for that in that region, your biomaterial is nothing but the supporting film.
Yes.
Okay. So there it will work. Now, which is purely biomaterial, there you can tweak this equation and that will work. But if you want to do all 3D thing from the projection where you have nanocrystal embedded in biomaterial, I have doubts. It may not work because the electron which is going through the nanoparticle and the electron which is going through the biomaterial, the channeling will be different. So together everything you cannot do 3D as of now.
Thank you, sir.
I think there's one question in the chat. So if we are doing it for biomolecules, is there any dependence on molecular weight or size?
No, basically no.
Okay.
Bigger size is always better, and as we see, if it doesn't affect the atomic weight, then molecular weight will also not happen.
Mani, you have a question?
Hello, sir. So I have two technical things would like to understand. One is what kind of detector do you use, and then
No, it's a camera only. It's a camera only, CCD camera. Image.
Okay.
Image, only image, nothing else.
Okay. And the total dose per tilt series
So,
or focus series?
So this is, you can see, I think it is written there, no? Okay. So for electron dose rate, for this is for silver, we have used 8 into 10 to the power 5 electron per nanometer square per second. So very low dose.
It's yeah, I think for biological sample it is really huge, it is nothing.
No, what is the electron dose rate you use?
We use maximum, let's say 30 to 50 electron per angstrom square per image, per field of view. So
No. I am talking about electron per nanometer square per second. Electron dose rate. Electron dose doesn't matter. Electron dose rate matters. Dose
rate
means per second.
Rate also it's around like 7 to 10 electron.
7 to 10 electron per
angstrom square per second.
Per angstrom square per second. Yeah, then the advantage is that if you use that, then you will have your see what electron dose rate works. So this is my atom. I have a potential which my electron is seeing. Now if you heat it up, the atom will vibrate. So my potential will be smeared out. So the electron as the temperature increases, the atom will move like this. So electron will see more, the potential will be smearing out. So if the potential, let's say I'm giving a value 10, then your electron may say see 5 eV. Let's say 10 eV, it is seeing 5 eV. In your case, when you are reducing the electron dose rate, your atom will not move much. So you will get better phase value. So you will get better. So it depends on if you can take the image. See, it is worse to have more electron dose rate, less as possible.
Yeah.
See, this is for crystalline sample. If you can reduce that, it's even better. If you have a high sensitive CCD camera, it is even better. So this method was developed for somebody has sent us question.
Yeah.
Thank you, sir.
Laser beam I cannot I can't say, because this method was used with for electron beam, because we are using electron channeling theory. Laser has a wavelength of around 300 to 400 nanometer, and I am talking to a wavelength of picometer. So it's a huge difference. So electron channeling theory cannot use for laser channeling theory. So that is different. So you have to, it's a different ball game, because if you change the wave, see, wave is wave. It may work. I don't know, but I never worked with laser, and it's much bigger wavelength, so it's a completely different ball game. This is for microscope EM only. Any other question?
And so just maybe because we were discussing the dose, so this high dose doesn't damage the structure?
High dose means it damages the structure, but at the same time it reduces your potential. So it reduces your phase value. So you really don't know what you are seeing. So So people take images, and that's why they increase the dose rate. But so the dose, whenever you increase the dose rate, you actually lose a lot of information.
Yeah, yeah.
So as low as
As
possible.
low as possible. I think so. If we don't have any further questions, let's thank Professor Somnath. Thank you very much.
Thank you.
Thank you, sir.
Thank
Thank
you.
you very much.
Thank you very much. Yeah.